Okay, good day, everyone. Thank you for attending my presentation. Today, I will talk about our work titled Quantum Multimodal Contrastive Learning Framework. And my name is Michael Qisen Chen, and I'm excited to share our research with you. This is an outline for today's presentation. And first, I will briefly introduce the motivation behind our work. Then I will go over related approach or purpose, method, experimental details, and finally share the results and conclusions. And here is the introduction. Our main motivation is to explore how we can combine the different multimodal into the quantum machine learning. And we take the EEG data, the image, as an example, and we using a single effective representation learning framework you can see on the right hand side. And some challenge is that EEG signal is often noisy and high dimensional. And we also have image which are high dimensional in a very different way. So our assume and our opportunity is quantum computing's probability may offer a more powerful feature extraction and representation capabilities across such different two modalities. And here is a relative work because there has been so many popular contrastive learning frameworks and models in the classical machine learning, deep learning fields like the clip, line, scene clear, etc. And typically they are unimodal or text to image. Here is very lack of the EEG to image and or time series to image representation multimodal constructive learning. Yeah, I have done several work like Muse Nerve last year, but here in this field still lack of research. And quantum machine learning has been explored for either image or time series but related combined. Like there are the single model is not a contrastive learning. They're just for the STM like EGNet and so far. And they show the promise on a small scale task. And our key step is combining the quantum encoders for EEG and image within a contrastive learning framework. And this is maybe the first quantum contrastive learning work to our best knowledge. And this is our proposed framework we call the Quantum Multimodal Contrastive Learning, QMCL. And this slide gives an overview of our framework. We have two separate encoding pipelines, one for the EEG signal and one for image. And our framework can to general to like end-to-end, any-to-any contrastive learning framework, but in the quantum one. And both pipeline include the quantum layers, and we use a contrastive objectives so that corresponding EEG to image pairs to get lie in the same embedding space to share layer representation. And here is our image encoder, image processing like quantum clip VIT. This is a traditional VIT here, and the thing we had done is to add a quantum neural network at the end of the traditional clip VIT module. And for here, we are use the pre-trained clip from the Hugging Face. So the thing is that we can to co-training this end-to-end with the EEG encoder we will introduce later. And here are our EEG content encoders. We have provided 4 content encoders on this task. One is Q-Nerformer. Yeah, all the encoders are the hybrid quantum classical neural network architecture. It's like for this part is the classical preprocessing module, and after this is a quantum time series quantum encoder. Yeah, the Q-Nerformer is like we have input the time series data like EEG. First, we do the instant normalization, and later we get into a 2 branch. One of the branches do the septural convolution, then do the self-attention, and they're like the transformer, right? And the other branch is to do the temporal convolution, then do the self-attention. And after the septural and temporal feature we have got, we will combine them to do the cross attention and to do the feed-forward layer like the transformer. Then after the classical one feature has been extracted, we will input the features into the quantum encoding layers and to do the prediction task. And another is the Q-Nerformer GA. The GA is just to change the instance normalization to the graph attention module. And there is the same as the Q-Nerformer on other architecture. And interestingly, we have found that the convolution maybe still works. So we also provide the spatial temporal convolution in quantum version, like the QST-conv. It's like this. We do the spectral convolution first, and then do the temporal convolution, and do the Batch normalization in EDU, and input the quantum encoding layers also. And the QST-conv GA is just put the graph attention in front of the QST-conv module. Yeah, there's 4 quantum encoders we provided. And let's go to the details of the quantum encoding layer. The quantum encoding layer, this slide shows how we embedded classical data into the quantum circuit. First, we load the classical feature into qubits with the RI rotations like this, and then apply the control-not gates in a ring pattern for entanglement. And finally, we do the feature measurement, use the poly-Z gates like this. And this step allowed us to capture rich representations beyond classical transformation alone, and embedding a classical feature into the high-dimensional Hilbert space. And this figure shows the quantum neural network we have used. We have used so many qubits and used the RY and gates and these control NAT gates. And we have done 4 layers quantum neural networks in our works. Okay, so let's through to the quantum multimodal contrastive learning, the whole framework. During training, we take EEG signal and image that corresponded to the same class or instance to push their embedding together. And we also use the influence loss for these works. This loss is very popular in the traditional classical constructed learning framework like Sinclair and Eclipse. And for this whole framework is end-to-end training. So the thing we need to do are to prepare the pre-trained clip weights and to use this pre-trained weight to get the image embedding and use the EEG encoder we have mentioned to get an EEG representation and to use this influency loss to align the different capacity and the different modality data representation together. And this is for the experimental detail. We use the scenes EEG dataset, which has the large number of images associated with EEG representations. There has 10 subjects and 16,000 near natural image. And all the EEG data are 64 channels and to do the 0 to 1 second post stimulus. And we train the 200 epochs on each models with weighted and optimizer with the learning rate like this. And for the quantum layer, we use 10 qubits and 4 layers QNN for this work. And here is a result. We can see that, be honestly, this is not so good, but even in the traditional classical neural networks or contrastive learning on this since EEG dataset, the performance are not so well too. So this is a very private exploration for this quirk in the quantum framework. We can see that the Kuhner former GA with gravitation performs the best in the 200 way zero shot complete classification on the both top 5 accuracy and top 1 accuracy on the average. So the overall performance remains a challenge. It is a top problem, but these improvements illustrate the promise of integrating quantum layers in the multimodal setups. Yeah. And these are conclusions. In summary, we introduced a very novel approach to leverage quantum encoders to improve multimodal constructed learning. We showed that the Kuhner former GA yields the top performance, indicated that the potential of quantum layers in very complex cross modality like EEG to image tasks. And this opens the door to further quantum-based approach in multi-sensor or multi-model data in the future, I hope. And here's our future work and discussion. And looking ahead, we plan to scale this model as quantum hardware measures and to see how additional modalities might benefit from quantum-enhanced constructed learning. And thank you for your attention. I'm happy to answer any questions by email or you can contact me with my information in the first slide. Yeah, thank you for your attention.